So today what we're going to talk about is one-sided limits and then what the intermediate value theorem is and how to use it. So what is a one-sided limit? One-sided limits mean that you're only looking at values approaching your C value from either the left or the right, so only on one side, not what the function's doing as on both sides as it approaches C. So we can take limits from either the right-hand side or the left-hand side. So a limit from the right-hand side is written like this. So you write your limit as usual, x with an arrow pointing towards C, but to indicate that it's only to the right-hand side, you put a little plus right there above C, and then f of x. So that means the limit as x approaches C from the right-hand side of f of x. So that means that you're looking at values that are just a little bit bigger than C. So if you were on a number line, if we put C there in the middle, you would be wanting to look at values that were on this side of C, so just a little bit bigger than C. So then left-hand sided limits, they're written almost the exact same way. So you write your limit with an x approaching C, but instead of putting that little plus sign there, we put a little minus sign, and then write f of x. And so again, if we drew a little number line, put C in the middle, it means that we're going to look at values to the left-hand side of C, so over here, or numbers that are just slightly smaller than C. And one-sided limits are really useful for functions that are only defined on one side of a C value, such as radical functions, which are functions that include square roots, cube roots, fourth roots, anything like that, or for when functions approach different numbers from the left and right-hand side of a number. So if you had a break and it jumped up from one value to another over a C value, your left and right-hand side limit would be a really great way to analyze what's going on and to kind of see more of what that function is doing. So now how do you actually take a one-sided limit? So for that, we're going to look at the limit as x approaches 2 with the negative sign, so that means we're coming from the left, and we're going to look at the function of the square root of 4 minus x squared. So in case you don't know what that looks like, what that is it's actually the top half of a circle with a radius of 2. So we're just going to draw a quick picture. So there we go. It's a rough picture of what this looks like. So if we're taking the limit as x approaches 2 from the left, we're looking like here. So we want to follow the function down from the left-hand side towards 2. So from the picture, you can see that the limit is going to be equal to 0. But say you had no picture, had no idea what that function was looking like, so you couldn't draw a picture, and say you didn't have a graphing calculator or you weren't allowed to use one, what else could you do? Well, you could use a numerical approach to solving this limit, just like we did before with full limits. So again, we're going to set up a table of values, so do x in the top row and f of x in the bottom. And instead of looking at values on both sides of 2, we're just going to look at values that are a little smaller. So we could start with something like 1.9, go to a little smaller and a little closer, so 1.99, get a little closer yet with just adding an extra 9, and then finally look at 2. So now what we're going to do is we're going to use our calculators to plug in those 4 different values into our function and see what sort of y values we get out and see if they seem to be approaching anything. So when we plug in 1.9 into our function, we get 0.6245. Okay, so then if we plug in 1.99, we get 0.1997. Okay, so we're getting smaller. And then if we plug in 1.999, we get to 0.0632, so even smaller. So just from those 3 numbers alone, it looks like the closer we get to 2, the smaller and smaller we get. So that goes along with our picture saying the closer you get to 2, the closer you get to 0. And 2 is actually defined for this function, and when we plug 2 into it, we get the square root of 0, or 0. So those are 2 different ways that you could do a one-sided limit. You could look at the picture, or you could do a chart, either way. Okay, so another type of function that one-sided limits are really useful with is what's called the greatest integer function. And the way that's indicated to you is it looks something like this. It looks like f of x is equal to brackets of x. And all it means to do is, if you plug in a value for x, it wants you to find the greatest integer that is smaller than x. So an example would be if you plugged 1.9 in, you'd have something like this. And the answer to this problem would be the biggest whole number that it's also smaller than 1.9. So 1.9 is really close to 2, but because 2 is bigger than 1.9, it's not actually the answer. We're going to round all the way down to 1. So what the greatest integer function really is it just tells you to round down to the next whole number. Even if you're at 1.9999999, the answer is still going to round down to 1. And this function is really great for one-sided limits because of how it looks on a graph. It actually looks kind of like a staircase. So if we draw a quick picture, so if we plugged in 0, we would get a 0 out, so we could put a closed dot at 0, and every number between 0 and 1 would also round down to 0. So we can put an open dot at 1 and draw a line across. Now when we hit 1, we jump all the way up to 1. So we can put a closed dot there because we can plug 1 in and get 1. And then every value over to 2 is going to round down to 1. So you can kind of see what the pattern is that it just kind of looks like a staircase with an open dot at one side and a closed dot at the other. So you can kind of see why one-sided limits would be really great here, because if we were taking, say, the limit of this function at 1, if we approach from the left, we're approaching 0, just like here, but if we approach it from the right, we're all the way up at 1. So the overall limit here does not exist, but we can look at what's happening individually on both sides of 1 to see what's going on. So now we're going to do an example of a one-sided limit that includes a greatest integer function as part of it. So what we're going to do is we're going to look at the limit as x approaches 2 from the right of this function right here. So 2x minus the greatest integer value of x. Okay, so if we're looking at numbers that are bigger than 2, but only slightly bigger, we're looking at values like 2.1, 2.01, and 2.001. So what we could do is we could set up another table and plug in those 3 different values and see what we were approaching, or we can kind of just think about what's happening. So if we plug 2 in, and anything that's just slightly bigger than 2, this piece right here is going to be really close or equal to 4. So now we just have to figure out what's going to happen at this piece, because we know from our limit properties that we can take the limit of each piece and then subtract them. So if we're looking at that greatest integer part, if we plug in anything that's just slightly bigger than 2, we're always going to round down to 2. So we can put a 2 right here. We have a minus sign in between, so our overall limit is going to be equal to 2. Okay, but you might say, well, Hillary, that was really easy. Just plugs in 2 to both pieces. But what would happen if you were looking at it from the left? So if I cross out that plus and put a minus. Well, if we're looking from the left, if we think about it, anything that's really close to 2 but on the left-hand side is also going to be really close to 4. So we can put another 4 there. But now we have to think about, are we going to have a 2 there for the second piece? Well, if you think about numbers that are close to 2 on the left-hand side, you have numbers like 1.9, 1.99, and 1.999. Well, if you plug those numbers into the greatest integer function, you have to round down. So you're actually going to round down to 1. So instead of having 2 as our limit, we're going to have 3. So you can see how the one-sided limits are really useful for the greatest integer function, because at whole numbers, you're going to have different jumps. You're going to have different limits. So it's just something to keep in mind and to think about when you do problems in case you see one of those symbols show up. So how do one-sided limits relate to your full limits? Well, one-sided limits actually affect whether or not the full limit is going to exist. So a full limit exists, or the limit is x approaches c with no extra signs or anything, of f of x. That exists if and only if, which in math is abbreviated as IFF, if the limit from the right exists, so limit as x approaches c from the right, if that exists, and it equals the limit as x approaches c from the left. So your right and your left-hand limits have to exist for that c value, and they don't just have to exist, they have to be equal to the same value. So what you saw in our last one, the limit from the right and the limit from the left were not equal to each other, but they both existed. So our full limit at x approaches 2 for the last example would not have existed. Okay, so one-sided limits also affect continuity on a closed interval. So we can say that a function f of x is continuous on a closed interval from a to b if it is continuous on the open interval from a to b, which just means that there's no holes, asymptotes, breaks, nothing in the graph on that interval. And if the limit approaching a from the right of f of x is equal to the function value at a, and if the limit approaching b from the left of f of x is equal to the function value at b. So a good example of this is actually the semicircle function that we looked at first. So we'll draw that really fast. So in case you can't remember, that function was the square root of 4 minus x squared. And our interval here would be from -2 to +2, with brackets so we include them. So to see if it's continuous on this closed interval, we first need to look at the open interval, which you can tell that there's no breaks or holes or anything in my graph, so it is continuous on the open interval from -2 to 2. So we could check that off our list. And now we need to look at what the limit approaching -2 from the right is and what the limit approaching +2 from the left is. So if we look at our graph, you can kind of tell that as we approach -2 down here, from the left-hand side, if we follow that graph down, it's going to 0, which is the same as the function value at -2. So that's good. So now if we look at the limit from +2 from the left-hand side, we're going to follow it down and we're also going to get 0, which is the same as the function value at 2. So here we can say that the function, the square root of 4 minus x squared is continuous on the closed interval from -2 to +2 because the right and left-hand limits of the endpoints match the function values of the endpoints, and it's continuous on the open interval in between those two numbers. So now getting down to the big theorem for this video, and that's the Intermediate Value Theorem, and it's sometimes abbreviated as IVT. And all it says is, let f of x be continuous on the closed interval from a to b, and if d is any value between f of a and f of b, so if d is a y value that's in between the y values for a and b, then there has to exist a number c between a and b such that f of c is equal to d. So what does that mean? So we can draw a picture real fast. Say we had a function like this. So we'll have a being down here, b being down here, and so over here is going to be f of a, and up here is going to be f of b. So all the intermediate value theorem says is that if I pick a number on the y-axis, say I pick a number that's right here, we'll label that as d. It says that if I pick a value in between f of a and f of b, as long as my function is continuous on the interval from a to b, that there has to be at least one c value that has that d as its y value, which we can see that this function is continuous. So if we go over here, so my c value would be right there. So the intermediate value theorem is great for figuring that out. It doesn't necessarily help you find where the c value is. You would actually have to set your equation equal to the d value and then solve for the x that gives that to you. But it can tell you that the number exists. So you might say, well, that's a great theorem, but how do I use it? So we're going to do an example right now to show you how to use it in a problem. So for this problem, we're going to use the intermediate value theorem to show that f of x equaling x cubed plus 2x minus 1 has a 0 on the interval from 0 to 1. So first, what does a 0 mean? A 0 means that the function has an x-intercept there, or the function has a y-coordinate of 0 at a certain x value. That's all a 0 is, it's an x-intercept. So according to the intermediate value theorem, first we have to see if the function is continuous. So because f of x is a polynomial, we can definitely say that it's continuous. So we can check that off of our list. So now what we need to do is we want to see what f of a is and f of b is. Well, a in this case is 0, so if we plug 0 into our function, we're going to get 0 cubed, which is 0, plus 2 times 0, so 0 again, minus 1. So we're going to get negative 1. And now I want to see what f of 1 is, or what the y value at our other endpoint is. So if we plug in 1, we get 1 cubed, which is 1, plus 2 times 1, or 2, minus 1. So if we simplify, we get 2. So we're looking to see if it has a 0, which means we want to know if there is a c value that gives us a d value of 0. Well, negative 1 is less than 0, which is less than 2. So because 0 is in between negative 1 and 2, or f of a and f of b, we can say that f of x definitely has a 0 on the interval from 0 to 1 by the intermediate value theorem. And that's because 0 is in between the two y-coordinates for the endpoints, so there has to be an x value in between 0 and 1 that would give you that y-coordinate of 0. So that's how you go about using the intermediate value theorem in a problem. I hope today was really useful for you, and I hope you have a great rest of your day. Thank you so much for watching.